Hi guys, so we're going to be solving this question. They want us to basically find the moment of inertia for this particular cross-sectional area member about the y and x centroidal axis. So they're already giving us an axis of reference for the moment of inertia. So the axis of reference is at this point. So we're going to stick to this point, try the entire calculation. That's very important. Now, the first thing I want you to understand is the concept. If you want to rotate a mass m from this point, that is, kind of like how the sun rotates around Earth, the mass is going to contribute its own inertia, and then there's also going to be an inertia as you want to try and rotate it about this point. So that inertia will be represented as the area of the mass times the distance between it squared. But if the mass is at the point at the axis of reference, at the point where you want to spin the mass, then the mass will only contribute its own inertia. There won't be any other inertia because the radius is going to be zero. So this concept is very important to understand. Now let's get into the question. So for the top rectangle, because we divided it, we're going to divide it into three shapes. This is the first rectangle, this is the second, and this is the third rectangle. So starting with the first rectangle, the inertia in the x-axis, since its center of gravity has a kind of radius away from the axis of reference for the moment of inertia, is going to contribute its own inertia, then the inertia if you're trying to spin it from a distance r away from it. Now the inertia of a rectangle is bd cube over 12, where b is the breadth and d is the height. B in this case is 100 and d in this case is 300. That will be 400 minus 100. So we'll just keep this. Plus the area times r squared. That is the area of the rectangle itself, which is 300 times 100 times the radius from this point to this point. Now for the inertia in the x-axis, you're actually considering the radius from the x-axis up to the centroid of that particular shape. Here to this position, it's simply going to be, we know from here to here is 50 because 100 minus 50, 100 divided by 2 is 50. Then from this point to this point, you know from here to here is 300. Therefore, half of it will just be 150. So it's going to be 150 plus 50, which is now 200 square because it's AR square. If you solve this out, you're going to get that this is equal to 1.90 times 10 raised by 9 millimeter 4. And this also has a y-axis inertia. You can see from this point to this point there is a radius. So to solve for it, the rectangle has its own inertia. This time to be db cube over 12. Yes, this is a proven formula. Plus the area of that shape, which is again 300 times 100 times the radius in this case from this point to this point, as mentioned earlier, will simply be from here to here. We know it's 300. So to simply get from this point, half point to here, you know here's 100. So 100 divided by 2, you know from here to here is now 50. So we can now simply say 300 minus this small area that we know is 50, which will give us 250. So from here to here is 250. That will be times 250 square. Solve this and you're going to get 1.9 times 10 raised by 9 millimeter 4. So I made a mistake here. This is supposed to be 1.425 times per 9 millimeter 4. Next, for the center rectangle, we're going to find the inertia in the x-axis, which is going to be its own inertia, which is going to be much simpler. So remember what I said. I said that if the mass is at the center of gravity of the mass and the reference axis for the moment of inertia are at the same point. Remember, it's only the inertia of the mass itself that will be calculated. So for this particular case, we know that the axis of reference is going directly through the center of gravity for this second rectangle. So all we need to solve is just for its own inertia, which is b d cube over 12, which is going to simply just be 600 times 100 cube over 12, which is going to 50 times 10 to the power 6 mm4. And then Iyy simply going to be, just switch it, EB3 cube over 12, which is going to be 100 times 600 cube, very large number, over 12 equals to 18,000 times 10 to the power 6 mm4. For the last rectangle, we don't need to resolving because the measure dimensions for this rectangle and the dimensions for this rectangle are exactly the same. If you resolve again for its inertia in the x and y axis, you will find it's the exact same answer as if you solve for this top rectangle. So there's no need for resolving it again. We'll simply multiply this by 2. So the total inertia in the x direction is going to be 2 times 1.4525 times 10 to the power 9. This is just to account for the fact that there are two rectangles with the same value, plus 50 times 10 to the power 6. I'm going to find the answer as 2.90 times 10 to the power 9 millimeter 4. And for Iyy, simply add the two you got. Remember, for this particular top rectangle, we got the value twice, 1.90 times 10 to the power 9 plus 1800 times 10 to the power 6, which is going to be equals to 5.60 times 10 to the power 9 mm4. Thank you for listening. Anything you do not understand, do not hesitate to ask in the comment section. Thank you.